So let me start out by saying that if you have questions, please interrupt me. I'd much rather that we have a lively dialogue than that I get through all of my slides and people don't appreciate what I'm trying to say. So today I'm going to be talking about a technique that you can use to detect bugs and, more importantly, to prevent bugs, which is namely pluggable type checking. It lets you write your own type checker for whatever properties you care about, and then run that as part of your normal compilation process. This is actually closely related to the discussion that we were having on the mailing list about dynamic languages and typed languages. In some sense, this is viewing Java as an untyped language, as a dynamic language that you can, in a principled way, add the sorts of types that you care about. So here's a motivation. This is a screenshot of a website, and the important thing about this is that the body of it is Java lang null pointer exception. This is not what you want your website to look like. Even though the code that created this passed the type checker, it was perfectly fine. So the problem is that Java's type checking is too weak. That is, it's incredibly useful, but it doesn't do enough. So it prevents a lot of bugs. For instance, it prevents you from assigning a string into an integer variable. The compiler is going to prevent you from doing that. The difficulty is that it doesn't prevent enough bugs. So here's an example. This is code that type checks, but if you run it, you're going to get a null pointer exception at runtime. Here's more code that type checks, and if you run it, you're going to get an unsupported operation exception at runtime. Now, these are actually the good cases. The bad cases are cases where the error doesn't show up, or you don't get an exception at runtime. For instance, suppose you create a date and put that into a map. Then you side effect the date and put that into the map too. Your map is now corrupted. And you're going to discover that at a much later time when you try to use it. As another example, if you execute a query, then this will throw an unsupported operation exception. And depending on what the user input is, it can throw a SQL exception as well. These are, again, things that we'd like to prevent to use it at compile time. We'd like to prevent this kind of code from type checking. And there are lots of other examples. You can have errors in your quality tests. You can have accidental use of uninitialized data values. You can have data in the wrong format. So how can we prevent these? The solution that I'm proposing is use of a pluggable type system. So the idea is, think about the properties that are important to you in your particular application, and then design a type system to solve that particular problem. Now, you write type qualifiers in your code. You can also have it happen automatically by using type inference if you like, so that you don't actually have to write anything. For instance, we can say immutable date equals new date. And now, if you try to make this side effect, you'll get a compile time error. Because you've said that that was immutable, but now you're trying to change it. Yeah, question?
So how are you going to know which methods are going to have side effects?
Okay. The way that you know that is that you have an annotated copy of the JDK. If you use our tool, you get an annotated copy of the JDK that tells you what all the methods that have side effects are. More specifically, it tells you for each method, does it change the receiver, does it change the first argument, does it change the second argument, etc. And so now your checking is modular, just like the compiler is. So in other words, all you need to see is all of your code and the interfaces of the things that you're going to use. There was another question here.
I was just going to say, so basically you can't use a third party that has it, you can't be using any third party libraries that haven't been annotated, right?
So that's a great question. If you use third party code that has not been annotated, then you have several possibilities. One possibility is you go in and annotate it all, just the signatures, you don't have to do the body. The second possibility is use a type inference tool that will automatically add the annotations. And we have a couple of type inference tools for some of the checkers that I'm going to show you.
Even without access to the source?
Yeah.
That's okay.
You need access to the bytecode, though, but you probably have that. And the third possibility is that you supply a compiler command line option that says, please ignore errors that are related to this particular library. Now, that's going to mean that you're going to find a set of problems in your code, but you no longer have a complete end-to-end guarantee, which you would expect. Yeah?
I suppose you could also use some AOP tool, right? Like, you know, so say like, oh, all methods starting with set, they should get the changes receiver, whatever.
Okay, yeah.
Mutation.
So you probably, I mean, AOP typically is a way of modifying behavior. Here, if you knew that fact, then you could just go and add all those annotations to the external library. You don't have to actually edit the external library. You can have a separate file that says what the annotations are in the external library, and then the tool will read it. Great, good questions. You're all thinking straight about this. Okay, so now, once you've decided what your type system is, that is what its rules should be, and you've written the type qualifiers in your code, then you just run the type checker like as usual. So for instance, here's a possible command line you might type, javac minus processor nullness checker, myfile.java, and minus processor is already built into Java. So this isn't a change in that sense. And that will output an error that looks just like any other compile time error. In this case, it says, you're using variable VB2, but I don't have a guarantee that's not null. So you might or might not get a runtime exception. Okay, so that's the motivation. Now I'm going to tell you about how you can write these annotations in your code. I'll then discuss some pluggable type checkers, and I'm going to give you demos as well. Then I'll tell you how you could write your own checker for some property that you care about. We distribute a number of these, but you probably have other ideas about what's important to you. And finally, I'll give a few conclusions. So Java 5 already introduced annotations, but only annotations on declarations. Java 7 permits you to annotate any use of a type, not just declarations. So you can say, for instance, that this string is untainted, the query that you're going to be executing. You can also say, this is a list of non-null strings. And this is the sort of thing you could have written in Java 5. The rest of them are not. You can say, this is a list of non-null strings. Or for instance, suppose you spent some time building up a graph, and now you know you're not going to change it anymore. You could then cast it to be immutable, and then guarantee that you don't make any modifications afterward. The compiler will look for those. And here's an existing Java class, and I've given you a better and more informative type for it. Unmodifiable list really implements read-only list of read-only t. In Java, the current Java says it implements list of t. Yeah?
You said the compiler will check it. How about dynamic languages and reflection?
Okay, so for one of our type systems, the one for reference immutability, it actually has some support for reflection. For all of the others, if you have things like casts, they'll warn you that you're doing a cast. But in general, they don't check reflection. In other words, reflection lets you do anything. Reflection lets you change the contents of a string, which is supposed to be immutable in Java. It lets you call any private method, etc. There's no way for a type system in general to figure out exactly what you're doing with reflection, whether it's evil or not.
Statically, but my question, I guess,
dynamically, I see.
Dynamically, it doesn't have any bearings on a runtime.
So if you're thinking about dynamically, these our checkers are intended to be run as compile time checks. You can imagine adding in, for instance, you could find all the places that it wasn't able to give you a guarantee. You could imagine turning all those into runtime checks. Our current tools don't do that, but it would be possible to do. Yeah, good question.
So what's an untainted string?
Oh, so typically people use the term tainting to indicate any data that's coming from the user or from an untrusted source is called tainted. And if it's guaranteed not, for instance, the user could type a JavaScript script as their string, and you don't want to just shove that into your HTML. Or they could type some kind of SQL injection attack into their string. You don't want to just concatenate that onto a SQL query.
So this is like trusted, right?
Yeah, sure. Untainted is the same as trusted. Yeah. I'll actually show you an example of a checker that works with that a little bit later. And typically, anything that comes in from the user is untrusted or tainted, and then you might have some validation routine that turns it into a trusted or untainted one. Good question. Thanks for catching me on the jargon. Oh, okay, so this is a Java 7 annotation syntax. But one cool thing about our tools is that they're backward compatible. You're allowed to write these annotations in the new locations in comments, and if you do, then our compiler will process them. And any normal compiler, say the Java 5 compiler or the Java 4 compiler that you're forced to use at work, will just ignore them. So you can get the benefits even if your coworkers or your boss don't want to use this. Okay, so why would you want to use these? There are a few advantages it gives. A big one is just better documentation. When you write code, you know whether you intend the fields to be null or not, or the return values to be null or not. Now you have an opportunity to write that down in a disciplined way. And furthermore, it's not just that it's documented, it's that it's automatically checked. So you're guaranteed the documentation stays up to date and it's still useful. It helps you find bugs in programs, find places where you've used, where your idea of what the specification should be is different than what the code actually does. Now, one thing that distinguishes this from a lot of other tools for finding bugs is that it aims to be complete. That is, it can give you a guarantee that all the code that you checked has no errors of a given type. It's not just trying to do some quick and dirty catch a few of the errors thing, but actually trying to show that there are none there. And this is modulo several things that people have already brought up. It's modulo use of reflection, and it's modulo code that you're not checking. For instance, because it's in an external library that you've said you're not going to check. It's also modulo native code and a few other things, also in those same categories. This can help you to do better optimization. It can also help you to do better analysis of other types. And another cool thing is that if you're doing a certain amount of checking statically in the compiler, then you can write fewer assertions. You can do fewer runtime checks. Okay, so so that's how you write these things, either now or in the future. And now let me tell you a little bit about the pluggable type checkers. So here are some of the sample checkers that are distributed with our set of tools. We have a checker that tells you if you have any possible null dereferences in your program. We have another one that tests interned, which tells you if you have any equality tests that are wrong. So interning may be familiar to you from the string.intern method that says if you have two strings that have the same abstract value, that is the same sequence of characters, you can make them actually point to exactly the same object. And that saves you space and it saves you time. And it also lets you document that these things are really guaranteed to be identical. We have checkers for checking whether you are accidentally doing side effects that you shouldn't, whether there's unexpected mutation. And we have a bunch of other simple checkers that you can create your own. So you can say whether a particular string is encrypted or not. If it's not encrypted, maybe that's not something you want to be passing over the wire. Yeah?
Can you make something immutable just for a period of time and then change it to not immutable? Like, basically, throughout this certain section of code, you want to guarantee that it doesn't change, but then you want to make it's okay if it changes afterwards.
So here's an example of when you might want to do that. Suppose that you have a data structure that you're building up and that you own, but you're about to call a method, and you don't want that method making any changes to it. So if that method has its parameter declared as read-only, then it is not allowed to make any changes. But of course, that doesn't affect your ability to change it. So we actually have two separate notions, one called read-only that lets this type of aliasing happen, and another one called immutable that does not let this type of aliasing happen. Now, you can't typically change something from immutable to one of the others without doing an unsafe cast, because immutable is trying to give you guarantees about aliasing, but you can do these others.
You had an example where you took a mutable variable and assigned it to a new variable and declared the new variable as immutable. your checker can then check that the new variable didn't get modified. But
Exactly.
then what if the old variable does? You can still modify it through the old variable, which points to the same thing.
Right, so in that case, the checker would give you a warning at the assignment saying that that's not, it would either say you can't do that, or it would, if you would put in a cast in explicitly, it would say this is an unchecked cast. So that's, so every type system has certain limitations. For every type system, there's code that behaves perfectly fine, but that the type system can't prove is fine. And that's a reason that even in Java 5, you still need casts sometimes. And these checkers let you put those casts in. What that means is, essentially, it says, every place there's a cast, it's your responsibility to think hard. And everywhere else, you don't have to worry about it. And that's also related to this notion, that's where the type system, you can have dynamism in the type system, even though it's a statically typed language. Okay, so we're talking about encrypted strings. We already discussed tainted or trusted. You can implement access control this way. You can also think about the encoding. For instance, this string is a SQL expression, or it's a URL, or is this string in ASCII or is it in Unicode, so that you don't get those messed up. Now, there are a bunch of people who are building checkers using our framework, using the syntax and the framework that we've built, and these are some of them. Yeah?
So could you elaborate a bit on the access control? What do you mean by...
Oh, so for instance, you might say this is a port that's allowed to receive data, or this is a port that's closed, as one example. So I'm not talking about Java access control like private, public, protected. Yeah?
How do you statically enforce the encoding?
You mean these?
Yeah.
Okay. This is the way you do it. And we'll be seeing examples, I think, not of encoding. But what you would say is, here's a method, and its argument has to be, say, ASCII. And then once you've written that annotation, you have to do that by hand, or maybe you have an inference tool that does it. But then now, whenever you're checking any of the callers of it, if they have something that is not ASCII and they try to make the call, then they'll get a compile time error. Now, suppose you get something from the user and you don't know whether that thing is ASCII or not, or it comes across the wire. So that's a place where you would actually have to have a method that checks it, and that would be a place that's unchecked. So typically, there's going to be some clever function that's going to actually be checking this, and you're going to have to trust that. That's a place where there will be a cast in your program. But that's only going to be at a very few places, hopefully exactly one, at the boundary of your system. And as I said, anywhere that there's a cast, that's an indication that you need to think hard about it and make sure that it's actually right. Because we're not going to write a type checker that can look at a method and say, aha, this is clearly a method that's validating that this is a legal SQL command, for example.
That seemed hard.
Yeah, I'm not that smart. Yeah.
So what's the advantage of using a URL annotation over just the URL class? Not passing around strings.
So you probably should do that, but that doesn't mean that all your code does. Okay? Great. So how do you use a checker? As I said, it's just a compiler plugin. There's already a system called annotation processors for doing these plugins. And they use exactly the same mechanism that the Java compiler does to issue errors. So after you've given this, then you get error messages this form, which is identical to what ordinary ones do, because it's using exactly the same interface. Okay, so let me, enough of talking about this. Let's actually see whether this thing works. Okay, so first I'm going to give you a... Okay, so here is some code. This is actually code from one of our checkers. So we've run all our checkers on themselves. This is something that is going to check uses of the new construct in Java, and it gets the path, it gets the method name, and then it asks, how is this method annotated? Essentially, it's asking, what are the annotations on this method? So let's run the type checker on this and see what happens. So there's an error. And it says the error is right here. It says there are incompatible types for method. The argument is nullable, but it's supposed to be non-null. In other words, if we were to look at annotations from element, and we can actually look at that if you want, then the annotation on that says method has to be non-null. But here, it turns out that enclosing symbol possibly returns null. So, in other words, this is a place where this method could go wrong because visit new array is calling it wrong. Yeah?
So you have both a nullable and a non-null annotation. So what's the default if there's no annotation?
Okay. So good. I've written a bunch of, I've written nullable here to make it clear, and also because you need to. The default is this. For everything except local variables, the default is non-null. For local variables, the default is nullable. And the reason for that is it turns out it dramatically reduces the number of annotations you need to write. Oftentimes in public interfaces, then you really intend things not to be null. But we have a flow-sensitive type refinement mechanism that if you have nullable annotations within a method, can often ignore them when it sees that you're actually assigning something that is non-null. So if you didn't understand that jargon, then don't worry about it. Essentially, it's non-null except for locals, and the reason is that that reduces the number of annotations you have to write dramatically. Yeah.
So you can have multiple annotations, right?
Oh, right. So I mean,
Something
you
could be
we can have-
nullable. I mean, one object can be several.
So you can't say this is a nullable non-null, but you could
No,
say
no,
it's
no. I mean, if
non-null
they're compatible.
and interned and read-only.
Exactly.
Not that I recommend you put a whole string.
Yeah.
I mean, so there's actually a serious question, right?
I mean, there
which
could be
is,
reasons
does this
for
clutter
why.
your code and make it totally unreadable? And I'm going to give you some statistics later on that suggest that that's actually not the case.
So for
Yeah.
the second argument, as far as annotations of others, that node, is the compiler smart enough to realize that is declared as nullable? It's really non-nullable because you had the assertion, or is it not able to?
Oh, this one?
Yeah,
Yep.
it figured out that it's not nullable.
Figured it out.
You tested. Okay.
Yeah. Okay. So that's a great point. Thank you for bringing that up because I had forgotten. So here we said that node is nullable, but then we wrote an assertion, and so now even if this needed to be non-null, it would be fine, because the compiler looks at if statements, it looks at assert statements, it looks at all other types of control flow, it looks at operations that themselves would only have succeeded if the thing was non-null, and after that, it assumes that it's non-null. That's this thing that I was calling local type refinement. So even if something has one type, then after an if or after an assert, it has the other type, until the compiler sees some expression that might change that. Great. Yes?
You had mentioned earlier that the compilation is modular so that you have an external description of a function like annotations from element if that's
Yeah.
in the library. Is that description complex enough that if that function has a conditional in it such that if you pass in a null, it might return a null, but if you're guaranteed to pass in a non-null, it's guaranteed to give you a non-null?
Yes, they can do that. So the question was, well, what you just asked was, can these annotations be polymorphic over qualifiers?
Yes.
Essentially, you said, can we show that if you pass in a non-null, you get out a non-null, if you pass in a nullable, you get out a nullable? And the answer is yes. So here's the actual declaration of that. And since we haven't written anything here, this has to be non-null, and that has to be non-null.
So you're saying in Java 7, it can be polymorphic on the annotations alone.
Correct. And let me clarify for a second. That is not part of Java 7. There are two separate things that I'm telling you about here. One is the mere ability to write annotations in new locations. That's part of Java 7. That's an official part of the language. The second is, what does a particular annotation mean? What does non-null mean? Or what does polymorphic over null mean? Or what does immutable mean? And that's defined by the checker that you choose to write. And that is not going to be standardized, set in stone at this time. You can use the ones you want. It's possible that this will be shipped by Sun as part of the JDK, but it will not be specified as part of Java. It will just be a useful external tool.
Right, but so if you have an annotation called X and an annotation called Y, and you have two T's, one of that only differ because one has a parameter with annotation X, and the other one has a annotation Y, it will be distinguished.
No. It will not be distinguishable. So any overloading like that is actually handled. Let me restate the question so that everyone understands. In Java, you can overload methods. So you can say you have foo of object and foo of integer. The question is, can you say foo of at x integer and foo of at y integer? And if you were running a compiler that didn't understand, I mean, if you had chosen to compile this, even with the Java 7 compiler, but you chose not to supply the processor argument, then it wouldn't know the difference between those. So for backward compatibility, though, that can't be legal, and it isn't. And that's why you need the polymorphism. That's why you need special annotations to indicate that there's polymorphism, because you can't write both of those. Good question. But essentially, that's a backward compatibility issue. Yeah.
I suppose these are just compile time annotations that are not preserved at runtime.
That's correct. So they will be carried through to the class file and all that, but especially the ones inside the body, you can't access it compile time because reflection doesn't generally have access to the body of a method.
Oh, I see.
I mean, you can always use reflection to look up the annotations on a signature. Okay, great questions. Okay, so let's go back to where we were. So here is that line that was no good. And it turns out that, so this can return null, so you've got to fix it. One way to fix it would be to change the definition of annotations from element, and the other is to change the call to annotations from element. And in this particular, so by the way, all these bugs are real bugs that we committed. And we didn't have our tools running yet because we were building the tools. So I'll show you the actual fix that we made, which is, oops, to add this. So this is saying if it's null, then you return, you say, there aren't any annotations there. And now when we run this, compilation is successful. So that's cool. There are two things that are cool about that. One thing that's cool about that is we don't have this potential problem, which we found out about because our checker that was trying to find null pointer exceptions threw a null pointer exception. The cooler thing about this, though, is there are no more possible null pointer exceptions in this code. Okay, let's look at another example. So here is a JUnit test, and it is just checking the behavior of JUnit 4.3 on null references. So we're asking if you say assert equals on null and the string null, should that test succeed or should that test fail?
Fail.
Yeah, it should fail. In fact, here's a hint. It says it should fail. It should throw an assertion error because this assert isn't going to be true. That's what it should do. What does it actually do? Let's see. I'm actually just going to run this. Wow, this is really horrible. But here's what happened. JUnit threw a null pointer exception.
Oh.
JUnit shouldn't do that. So let's see if we can figure out what happened. Here's the code for JUnit, and let's run the Nullness checker on it. So it's telling us about some problems. So here's an example. It says expected might be null, and we're calling it here. So in this case, we're dereferencing it right here. In this case, this is a private method. If you go look at all the places that this is called, it's actually never called with a non-null value. So the right way to fix this is just by saying, oops. Now, in some sense, I haven't really fixed anything about the code, but I have documented it. Let's see the other errors. Okay, here is an example where we say if o1.getClass is array, so in other words, if o1 is an array and o2 is an array, et cetera, et cetera, et cetera. But it turns out that o1 and o2 could be null. That's perfectly legal. So the code that should really have been there was this. Oops. So let's let's look at the last problem, which is very similar. You're formatting an object, and you're saying, we want to print out the name of that object. The name of the class of that object. But that object could be null. So the right thing to do here is to, if it's null, print the value null, and otherwise continue. So that is the last error. I already fixed that one. So let's, whoops. So let's rerun the checker. And those were all the errors in that. Those are in JUnit 4.3 that have since been fixed in exactly this way. Okay, so that was nullness. Questions about the nullness checker? Yeah.
So would your JUnit, the actual test you wrote, now fail because it's?
Oh, great! I forgot to do that part of the demo, didn't I?
Yeah.
Should fail.
Yeah.
So it succeeded because I said I expect this test to fail. So JUnit does the right thing. So this says we expect the test to throw an insertion error. If the test had not thrown an insertion error, JUnit would have said test failed. In this case, it says test succeeded because the test did what I said the test was supposed to do. That's the way you write a test that's expected to fail in JUnit.
But why didn't it fail to compile though? Wasn't it? Didn't you just change the cert equals to change the quality?
That was
not
a-
be
that was a-
null?
That was the second part. There's two
Oh, was that
parts
different
that
part?
changed.
That was the private.
Right. The private one I changed. The
Oh, okay.
public one
Public one you
I
kept.
left. Right. Yeah. Okay. Great. Sorry. Thanks.
So there's two things. There's test equality and test arrays, right? Because you changed two things in there.
I changed 3.
Yeah,
Actually.
oh, okay.
I changed the private one, and then I changed 2 public ones
Okay.
for these 2 problems. One for test equality and one for test arrays. Okay. Great. So good. That's nullness. Let me show you a demo of the mutation tests. So again, I'm going to show you. Actually, that's fine. I'm going to show you code from. Oh, yes.
I was just wondering, do you have plugins for Eclipse or IntelliJ that will show you these annotations on the quick docs stuff?
So I'm not using Eclipse because I have a marvelous power to make Eclipse crash during demos. We have an Eclipse plugin. It is not perfect. There are people working on improving it. I know of people who use it. It has some problems.
And the IntelliJ?
If you're using Eclipse, then I would strongly urge you to use the annotations and comments feature, because Eclipse, of course, it hasn't been updated for Java 7. So it would tell you syntax errors all over the place. IntelliJ, in their, I think either June or July, I can look up the exact date, then it will actually understand the syntax. I can look up the exact date for you. Okay, so this again is part of our framework for doing these checkers. This is something called annotation location. So it tells you things like, suppose you have a list of arrays and that thing has 2 generic parameters and there's an annotation deep down in the middle of it. How do you how do you say exactly where in that big complicated type the annotation actually sits? And the way that it does that is it has a list of integers, and essentially the integers tell you, you take the third parameter and then you take the first list level, etc. Now you notice that this class is immutable. We do not want annotation locations jumping all over the program. That would be not good. And then just for emphasis, I've written immutable here, though you wouldn't have to given that it's up there. So this is the internal representation. So let's see what happens if we run the checker on this. So, bummer, there's an error. So it's complaining about this line. Remember, I showed you the location field, and the location field was supposed to be immutable. Now, here, I'm creating collections.unmodifiable list of location. So, what could possibly go wrong here? I said the thing was supposed to be immutable, and I'm calling collections.unmodifiable list.
So it looks like there's a little bit of a difference with the way that you're using immutable than, like I thought of, like with final, right? Where objects that are parts of that object can be changed generally, right? But with immutable, they can't. It seems like, right?
That's correct.
Okay.
Thanks for bringing that up. So the immutability we're talking about here is not the shallow immutability of the top level of your data structure.
All the way through. Anything
Abstract value. So you can explicitly exclude state fields from the abstract state. So ordinarily, immutability applies to the entire abstract state. And you can say, for instance, this field is a cache, or this field is transient or something, and then you can say, please don't count that field. But by default, all fields are included.
And so with that, when you had said we didn't need to specify for this property on there that it was immutable because the class is immutable, it's because it's all inherited all the way down.
Bingo.
So you can say, you can put an annotation in there mutable or something
Yes.
for specific ones?
In fact, that's exactly how it's spelled.
Okay.
Yep. Good question.
Is that why that issue is happening, that line? Or
No.
Okay.
It's a good guess, though. So what's happening here, what we want is that this dot location can't change out from under us. We called collections.unmodifiable list, but what could go wrong here?
Unmodifiable list, collections.unmodifiable list is just a proxying wrapper. It doesn't actually protect you from the underlying list being mutated.
Right. That's exactly right. Did people hear that?
Yep.
So the difficulty is that someone else could have a pointer to this thing, and they could change that. You won't be able to make modifications through this, but someone else could. So this is related to the difference. I was telling you about the difference between reference immutability and object immutability. This is trying to guarantee object immutability. You don't want the abstract value to change out from under you. And that's why this here is the right fix, which is make a copy, and we'll throw the immutable annotation on that, saying that it's a brand new copy, so it's safe to do that because there are no aliases to it. And this is sort of like just putting a cast here, but it doesn't raise any warnings about, hey, you're casting.
So that add immutable is actually required there?
Yes, because if you just create a new array list, by default, that's mutable. I mean, backward compatibility, in Java, if you create a new list, that's a mutable list. If you want something different, we have to say it.
Right, but I thought that the location variable itself was flagged as immutable.
Correct, it is.
And so the initial set in the constructor doesn't count as part of the immutability.
No. Okay, so let me make an important distinction between assignment and mutation. This field is immutable. You can set this dot location equals whatever 100 times in your program, as long as you always set it to an immutable value. You can assign it. Assignment is controlled via final and a new annotation we've added. Mutation is controlled by immutable and mutable, which are two annotations we've added. So Java in the past only had control over assignment, and only in one direction, which was all it needed. Now, with our pluggable checker, it has control over assignment in both directions and over mutation in both directions. That's a great question.
So
Yeah.
you had said something about doing a deep immutability. If those had been a list of objects, would this then fail?
If,
I mean, integers are immutable, so therefore there's an implicit copy. You don't need to
I
worry
see.
about copying the members.
okay, so good question. It would not fail, and the reason is that it's deep, except for generics where you're explicitly specifying the type. If you're explicitly specifying the type, you get to say whatever you want here. And if you have a list, you can say list of non-null, you can say list of nullable, you can say list of immutable dates, you can say list of mutable dates. So if the type is explicitly noted here, then you note it explicitly. If it's just a field, then it's inherited. So the same thing goes for arrays. You can mark each level of an array independently, but all the fields inherit from the object.
So you can
And
say,
it turns out that that's what you want in terms of flexibility and in terms of minimizing annotations in the usual case.
so you can say an immutable list of mutable dates.
Absolutely. And what that means is that you can't change the list. The list always contains the exact same objects. But of course, those objects can get updated. They can't get pulled out and a new one put in.
Right.
Yeah.
So I take it then it picked up on the fact that integer is immutable inherently. If you had gone crazy and created a new array list, and then instead of marking it, annotating it as immutable, put it inside of an unmodifiable list, given its knowledge of the libraries, would that have passed?
So if you had done that in our current implementation, it would not have passed because of a limitation in the way that polymorphic qualifiers are parsed. But we're working on fixing that. In particular, some of our checkers handle that, and this checker doesn't happen to handle that at the moment. So yes, it can be done. We have done it. It doesn't have to be done on this one. And it's on our to-do list. Good question. I mean, and in fact, that may be what you want to do. Because the cool thing about this was it gave you dynamic checking. The cool thing about this is it gives you static checking. Now, if you're compiling your entire program with the pluggable type checker, this is perfectly fine. But if it might link against third-party code that hasn't necessarily been run through the type checker, you might want both. Okay, so if we check this now, then it passes. So that was a correctness issue. And we actually had annotations that were jumping all over the program. It was, as compilation went forward because of someone was keeping hold of one of these and modifying it afterward. So that was about correctness. Now let me show you optimization. So here is a class. Let me page up so you can see the name of the class is Annotated Type Factory. Essentially, this is the thing that, given an AST node, tells you what is the type on that AST node. And here is an optimization. It says this is a map that given an AST node, like new or a method call or something, remembers what the type is so that you don't have to recompute it all the time. Now, if you have a map, then the values in that should be immutable. Because if they're not, then things can go wrong. So let's see what happens if we test whether this optimization is properly implemented. It's not. So here is the getter, and it looks a lot like the standard getters. It says if the cache contains it, then just return that. Otherwise, compute it, put it in the cache, and then return it. I'm sorry if that went too fast.
I didn't quite understand what's the issue with having the value change. I mean, I understand the key can change, but why can't the value not change?
Oh, right, that will not corrupt the map. So if the key changes, it corrupts the map. If the value changes, then the abstraction is just broken.
Oh,
because if you put something in it, you expect to get the same thing back out. Thanks for asking that. So essentially this says, if we want to get the type on an AST node, then we say, is that in the cache? And if it is, just return it from the cache. Otherwise, you compute it. That's these two lines. Then you put it into the cache, and then finally you return it. So the error down here says this does not work. Get is returning. It's found an immutable annotation type here, but it expected immutable annotation type here. I'm sorry, annotated type here. In other words, get annotated type says it's going to return something that clients are allowed to mutate. The default is mutable. That's backward compatible with Java. The difficulty here is you're returning a pointer to a value that's in the cache. And once it's returned from here, people can side effect it all they want. And now you can try to pull the thing out of the cache and you get a different value than the one you put in. That is, it would be the same object, but it would be a different value, which is not what you want. So the solution to this is that when you return an element, you should copy it and when you put it into the cache, you should also copy it. Oops. So you need to do this, you need to do both of these because you're returning a reference to that, and now people can side effect the reference. I mean, we can't control what other people are going to do with the thing we're returning. Now we know that they're going to be modifying something that doesn't hurt us. Now the alternative is, we could have said that this is immutable. That would have forced us to change client code. It's acceptable. In this case, we didn't want to change the interface. Yeah?
Here could seem neat if we could check at runtime whether an object we get is all immutable.
Okay, so this notion of immutability does not have any runtime representation. So there are certain things like string that are immutable, but we're letting you put immutable on any class at all, even the mutable ones. And we're not adding any runtime cost at all. You run this on a standard JVM with no extra fields, no extra bits. So in general, there's not a way of testing that. You could imagine having a class loader or some other mechanism that would add in that kind of representation. Our current tools don't do that because we don't want to pay that cost.
Yeah. I mean, here you're just on the actually check, did this object have the this annotation attached to it?
Objects don't have annotations attached to them. Types in your program have
yeah.
annotations attached to them. Runtime classes of objects don't have annotations attached to them. So for instance, if I have a date in my hand, its class is date. Its type in the program might be mutable date, might be immutable date. I don't know. That was a long time ago. That was compile time. I don't have any runtime representation of that at all.
Certain annotation types, you can preserve the annotation on, make the annotation that's on the class available
But that's
at
not on a
runtime.
class, it's on an instance.
But exactly, yes, I don't know like if in Java 7 there is some fancy new mechanism to get instance level annotations.
No, that would require extra information to be carried along at runtime, and we decided that was not worth it.
Yeah, but
there,
so
it's definitely, there are situations where it's a great thing to do. But those are situations where you should use some bytecode rewriting or something.
Yeah, but so even in Java 7 it wouldn't even be possible.
It's not built in, no. You would need to rewrite the bytecode or something like that. And there are situations where you want to do that, but it's not the default. Yeah.
So could you declare element as immutable instead of the deep copies you change?
So declare this element as immutable?
Right.
Well, the issue is we're worried about the annotated type. This is the key that's being used in the map, but we're worried about the values.
Okay.
In this particular case, I mean, you really don't want either one to be changed. And all I'm doing at this point is making sure that the values don't change, not that the keys don't change.
Okay, so that's
Preventing
what
the keys
you're
from changing, it's a whole different kettle of fish.
You could annotate the return value as immutable.
Yes.
And then you wouldn't have to make those changes.
Correct. Right. So you have two options. One is to put these two deep copies that I just showed you. The other is to put immutable here, which may force you to change plans.
Right.
You had a question?
I was going to ask something right along that line, because that was the first thought that sprang to my head was declaring the return type as immutable.
And the reason is that there was a bunch of client code that found it convenient to make changes. So which design is better? I don't know, but you can express the one you're talking about. And now we know, right? You can just look at this code and see that this thing is in fact mutable. Yeah.
But if clients expected to change elements in a cache, they probably supposed to share those changes, and now they are invisible.
Okay, so in this particular design, they are not supposed to do any such thing. You could imagine a design where that was the case, and in that case, you wouldn't want to do these copies. I mean, what you're doing is you have the ability to express what your design is and have the correctness of the code with respect to that design checked at compile time. So the design you're proposing is a reasonable design. It's not the design of this code. And if you did that, this code would be wrong.
Although that's not really captured. I mean, those two alternatives look the same, don't they, in terms of the type annotations?
Well, if you go back up to the top, here we wouldn't have written immutable right here. That's a way that, in which it would be different.
In fact, you might put mutable there if you wanted to make sure that people realize that could be changed.
Right. Putting mutable there would be redundant, but you are permitted to do it for emphasis.
As a documentation.
Exactly.
But I think you said that clients found it useful to mutate those values.
They found it useful to mutate them, but that does not mean that. So they found it useful to take a copy and mutate it.
Okay.
So for instance, they said, what's the type of this thing? And then they did some kind of analysis on it. And they were storing the results of their analysis. Or they were saying, okay, that one was a non-null integer. Now I want to create an array of non-null integers. Did you have a question that was queued up a little while ago?
Well, here was just so if I understood correctly, putting like immutable on the element that's passed in wouldn't really protect the key, because someone could have a mutable reference and cast it to immutable and pass it in, right?
So if you're doing casts, then you can't control anything. But if it was marked as immutable, then that would mean that no one in the world, and in the absence of casts and unchecked code and native code and reflection, if you have something that says immutable, no one in the world can modify it. No one in the world has an alias to it that is permitted to be changed. Okay, great. So
understand that you shouldn't cast immutable to mutable. That would trigger some warning. But casting a mutable to a immutable, because you want to pass it into some function that's not supposed to change anything, but you still have a mutable reference.
So that's also bad, because remember, immutable says no one in the world can change this. Now there's something called read-only that says I can't change it, but someone else can. So you can go from immutable to read only, or from mutable to read only. And that doesn't even require a cast. It's like, suppose you have an object variable. You can assign an integer into that object variable. That doesn't require a cast, because it's a supertype. Read only is a supertype of the other two. So it's just legal. Great, I see people nodding. That makes me very happy. Because some people don't get that. But if you don't yet, you will soon. Okay, so that was that demo. Thanks for all the good questions. That's probably the most fun I've had giving that demo so far. Okay, so I've shown you that in a canned demo situation, these checkers work great. Let me tell you a little bit more about using them in real life. We've run them on multiple code bases that are more than 200,000 lines of code. And every time I run the checkers, every time I run any checker on any code base, it always finds errors. Sometimes it finds important errors, sometimes it finds dumb errors. It always finds errors, and it finds important errors enough. And by these I mean ones that a human being thought was important enough to fix. Yeah?
So if you were to run this on a project that had 200,000 lines of code that didn't have any annotations to start with, would you get a lot of noise that you have to go through and fix, put in a lot of annotations before you get anything useful?
Oh yeah, it'd be miserable.
So practically speaking, you say it scales up to 200,000 lines of code, but that means that you started small and worked your way up to 200,000.
No. So you have three options. One option is choose from your code base a small part of the code that you really care about, annotate that, and live with casts or warnings on the boundary of it. And you could then scale up later. Another possibility is, for instance, maybe you have a big system, but it only uses encrypted data in a small part of it. You can imagine annotating the whole thing, all uses of encrypted data, but it's not going to be that many annotations on your entire code base. And then a great way to approach this is you have your huge code base, run type inference on it, have it tell you all the types, or at least have it get 90% of them right for you, and then you can just fine-tune or correct the places that it got the inference wrong.
So when you say the checkers are effective to 200,000 lines of code, are the type inference tools scalable to 200,000 lines of code?
Yes, they are.
Okay, because the tools was good.
Yeah. That's good. Yeah.
Can you actually define what you mean by the fact that this scales to 200,000 lines? I mean,
So I'm not really talking about the speed of the checker so much, though the speed of the checker is fine. It is less slow than, when you add that into Java type checking, it's still the same order of magnitude of speed. What I really mean is that...
No out-of-memory error.
They're actually, if you try to run it on sufficiently huge code bases, you may get an out-of-memory error because it's actually carrying along more information than the Java compiler usually does. What I really mean is that there are a lot of tools that can work on a very small code base, but a code base this size is interesting not just because it's big, but because it probably has a lot of variety. There's probably any code base that big probably has really weird uses of generics. It probably has interesting control flow structures, that kind of thing. So what I really mean is that it can handle a large diversity of code, in addition to being performant. So yeah.
one more question. For I would call it a medium-sized code base, say 5,000 lines of code. How much extra memory how much memory would this actually need to be able to run the type checking on that?
5,000 lines of code is not going to be a problem.
Okay.
We're talking about stuff this big, and I just changed the -xmx argument to Java C to not default to something puny.
Yeah.
A few megabytes more was fine, as I recall. Don't quote me on that. I can look up my Java C settings.
Okay, so basically, on a normal development box, you're not going to need to add extra space or something.
Oh no! All you'll have to do is change the -xmx flag.
Okay.
Yeah.
What does it do in the face of use of frameworks, especially frameworks that use massive amounts of proxies, and especially there are a few running around now that like the modification? It sounds like
Right. So our system, I mean, bytecode modification is sort of in the realm of reflection. I mean, our system is going to check the code that it sees. In terms of frameworks with a lot of proxies, I think you have a bigger problem in terms of the framework you needing to do annotation on the framework than the fact that it uses proxies.
Would there ever be a case where the checker might report something as being a problem when it's not because there's stuff happening at reflection and runtime and stuff?
So with respect to reflection, it's more likely that the checker would give you a false negative. That is, it would think the code was what it was, but you're actually doing something tricky and evil at runtime.
Oh.
The checkers do sometimes report a false positive. That is, they say, ooh, I can't prove that this thing is non-null. And you say, oh, but right here it you know, has some obscure test that I can figure out as a human, but that is beyond the ability of a type checking tool. Yeah?
I'm probably jumping ahead here, but
I'll stop you if you are.
Are you certifying, or is there any kind of a certification check look over of these checkers that are coming on? Is anybody looking? You listed a whole bunch of universities that are writing these things. Is anybody looking at them to see whether they're, you know, quality control kind of things?
So you're welcome to download them. Everything is open source and freely available. We find bugs in them, absolutely.
I imagine you would learn a lot by comparing them.
Yes, and in fact, I've been doing that. There are various other academic tools that are intended to do inference or checking. None of them scale. It's been a problem. We've been able to compare on small code bases, and that has not revealed problems in our framework. Yeah.
Is it compatible with Groovy C compiler?
Okay, that's a great question. Right now, currently, it is compatible with Java C. So for instance, if you want to use this in Eclipse, the way that you do it is to have an external builder or to use Java C as your builder. That will be changing in the future, but that's the way it works now. Essentially, it would be extra implementation effort to target all of these other compilers, and we haven't got the manpower to do that right now. I mean, the other thing that you can do is just you do your ordinary compilation, and periodically you can also run the checker. So, of course, it's better if it runs on every compile. That's what you really want. Yeah.
You said some of the other approaches don't scale. What causes them not to scale?
Sometimes it's because they're using really heroic and tricky static analysis that is too time-intensive or memory-intensive. Sometimes it's because they just haven't thought about issues like generics because that didn't seem that interesting to them, though it turns out to be important and very tricky in practice. And sometimes it's just because they built something that was good enough for them to get a paper out. And hey, I love getting papers out. But I'm also interested in changing the way people think. And I believe if you put a tool in the hands of users, they teach you a tremendous amount. You learn a vast amount. Yeah.
So I'm still trying to get a handle on how effective this is for a production program. You mentioned that you found errors in each code base you ran on. I'm curious if you ran on a significant code base that already had a good suite of unit tests, that they'd run find bugs on, you know, that they'd already gone through their normal quality control.
Let me answer that question in the next couple slides. I've gotten a little bogged down here, though these are all great questions. I mean, and if there's stuff that I want to address later, I'll address later, so keep asking them. And if I don't answer your question, please ask it again. Okay. Yeah.
So I was going to ask something, and you might cover it with that, but you say that you ran it on systems that have over 200,000 lines of code. So those are existing systems that didn't have annotations in them. And so if you run it against something that has no annotations on it, it's not going to verify anything at first, right? I mean, you have to put the annotations in it or use the inference, right?
There are two different types of checkers. Some checkers, if you run them on completely unannotated code, they spew out a zillion errors.
Okay.
The nullness one is like that. Every dereference in your entire program, it'll say, whoa, that might be null. There are other checkers where if you run them on unannotated code, they pass and say, everything looks perfect. Mutation is like that. The default is mutable.
So it depends on which checkers you're using, right?
And the default settings.
Okay. Okay.
So you just run one at a time? Your examples only have one checker.
Yeah, there's no reason you couldn't run more than one at a time. I personally only run one at a time. I'm trying to remember whether there is an issue with running. At one time, there was an issue with running more than one at a time in your implementation. I don't remember whether it's still true or not.
Wouldn't the errors be interspersed, or I mean?
Yeah, but that's okay. I mean, they'd all be in order in terms of line number.
Yeah,
but it would say, you know, here you have an unchecked cast, here you have a wrong argument, here you have a nullness error, here you have a mutability error.
It seems like if you did those sequentially and you had 7 of them or whatever, however many checkers you were going to run on there, it would take a lot longer than doing them all along the way, right?
So I'm not saying that that's a long-term solution.
Okay.
And I'm actually very interested to see whether people end up running 7 of them or not.
Well,
So
I would think
I could
that
imagine
you might, right?
I could imagine that there are people who really get into this and want to run 7 or more of them.
Mm-hmm.
And I could imagine that people say, okay, you know, in my environment, so I've had people on Wall Street tell me, in my environment, null pointer errors are a big, big deal. I've also had people tell me, in my environment, null pointers are not a big deal. I just don't want to be bothered with that. But mutability errors, I find those bite me all the time. So I'm not telling you have to use these. You've got to decide. That's your policy decision. And so I'm going to find it interesting to see how many of these on average people use. I don't know.
You can use different checkers on different days, like nullness check on Monday.
Really, you want to run them all every time you compile. You know, you don't want to wait a week before you realize you've introduced some fundamental design error. Okay, let's move on. Okay, so what if you had a code base on which find bugs had been run, for example? So here's a 4,000-line program. It was the biggest that that I was willing to run these other tools on because they were a pain. The check and they had some issues with other code bases. This is just looking. So this program is only 4,500 lines. The checker framework found 8 errors. The cool thing is we know that it didn't miss any by design. It also gave 4 false warnings. So in other words, it gave 12 warnings, of which 2/3 were real, and the other 4 were things that you had to suppress with an annotation or a cast or something. Or in this case, we just put an assert not equal null 4 times in the code. And a human had to write 35 annotations. This is without any 35 annotations over 4,000 lines. And this is without use of any inference, because the inference didn't exist when we did this particular study.
So writing those annotations, was that iterative? You run it,
Yeah.
you see some, okay.
Yeah, exactly. You run it, it issues some warnings. You say, oh, well, this parameter should have been non-null, so you add that.
So the 8 and the 4 are after putting in the 35 annotations, that's what you were left with.
Yeah, so here I'm not including any suppress warnings or asserts here.
All right.
Great question. Thanks for keeping me honest. So then we ran find bugs. Find bugs reported 0 warnings. So in other words, it missed 8 errors. It issued 1 false positive. It wins in this column, clearly. I mean, find bugs, it has a different philosophy. Find bugs is a useful tool for certain circumstances and for certain uses. And of course, it does a lot more than null pointer checking too. Find bugs will find the really egregious errors. It does a very shallow analysis to find the low-hanging fruit. And it's good at that. We also ran JLint and PMD, and JLint gave 8 false warnings and didn't find any of the real errors. And PMD just didn't say anything at all. Again, these don't require you to write those annotations. Though I would argue that writing the annotations gives you some benefit.
Yeah, really.
Yeah.
I'm sorry, I think I misunderstood the comment. You said you had to write, you had to write 35 annotations to kill the 8 issues, or you wrote 35 issues and then you ran it and found 8 null pointer errors?
Here's what happened. We ran it. It output like 20, 30, 40 issues, something like that. We looked at them and realized a lot of those are false positives that we could eliminate by just writing at non-null on a parameter, for example. When we were done with all that, there were 35 places we had to write at non-null or at nullable on a parameter or a generic or something like that. at that point, there were 12 warnings left where that weren't false positives, that should just be eliminated by writing an annotation. Of those, 4 of them we eliminated, or we did a human hand analysis of the code, determined that it could never go wrong at runtime, though there was a complicated reason. So here's an example of something that might happen. It actually did happen in this particular thing. There was a pair of regular expressions. One was for the start, and one was for the end. And they could be null, and if they were null, they were both null. Or they could both be non-null. And there was a piece of code that tested whether the start regular expression was null or not. And if it was not null, then it matched both the start and the end regular expressions. And the checker said, oh, the end regular expression, that one might be null. I haven't seen you check that. But if you were to look at all the code, all the places that they get set, then whenever the one was set to non-null, the other was always set to non-null. So that's a fact about the program that was beyond the scope of the type checker. And so there we said, if start regular expression is not equal to null, assert end regular expression is not equal to null. We added that assertion. And then the rest of the code type checked properly. So that was one of these 4. Does that make sense? You don't look 100% satisfied.
Well, I would actually say that in that case, on running the type checker, you have 39 false positives that you had to shut up.
Yeah. So, I mean, but these, well, that was on running it on a completely unannotated code base.
Right.
Yeah, maybe you should give like 2 rows with 0 annotations written, so many false warnings, and what do you have here?
Because initially when you ran it, there was like 39 issues, but then you
Well,
went and took care of
There
it.
weren't
There's
necessarily
30
39.
There's
There
actually
were
37
different-
issues, 8 of which were actual real problems, and the other, or there's 40.
But, I mean, okay, so how long did it
47
take?
actual problems, yeah. Hold on,
How
I gotta
long-
do math late today. Hold on.
Here's probably
How
the
long did it
confusing
take-
part.
Hold on. How long did it take to deal with these? Like 2 seconds apiece. How long did it take to deal with these? Long time. Sat there, looked at every path through the entire program. How long did it take to deal with these? Even longer, trying to figure out what the hell someone was thinking when they wrote that code to begin with. Oh, that was wrong. The time for these way dominates the time for this. These were all the easy ones.
So
And half the time you just looked at a comment that was in English, and you just translated that into an annotation.
Okay. So for those 35, you ran it once, you got this list of about 40 or 50 messages. For each one, you just looked at it, looked at the line, said, oh yeah, that's obvious, put an annotation, looked at the next one.
Bingo. That's exactly correct.
Still a false positive. I mean, it's quickly resolved false positive,
Right.
but it's a false positive.
The other way to look at it is that your program was wrong. You had written the wrong types. That's like saying you started out with all object in everywhere in your code, and you haven't yet changed it to what the types really are.
Yeah, I don't want to get direct. Don't want to really argue that point, but then I would say that I wouldn't have needed 35 annotations to. That would have meant I would have had to correct the code.
Right, and
Well,
these are
the
correcting the code.
annotations are the code.
These are writing the correct type. Your types were wrong in your program. This is writing the right types. Once you've written the correct types, and every type in the program is an honest representation of the values that can be there, then you have 4 false warnings, and there were 8 real errors. Yeah.
So for a new program that you're developing or something, this sounds a great idea and everything, but if you're dealing with an existing code base, it could be a decent amount of time
Yes.
refactoring that build, isn't
I
it?
mean, and that's a case where you probably want to use type inference, and you want to start in the critical parts of your code.
Yeah, yeah.
Right? You know where the problems are in your code. You know where you need a little extra attention. So I'd also like to point out that the number of annotations you write is much less in new code. That's because in new code, you're actually thinking about this stuff, and and this is forcing you to use a slightly better design. And that's something I'll get to in a second.
Can you scope the checker to only look at certain parts of your code? I mean, it's kind of a
Yeah.
feature.
I mean, you could just supply those arguments on the
Right.
command line.
Okay.
There are command line arguments to tell it to ignore, calls into certain libraries, etc.
Cool.
Okay. So the checkers are actually fairly rich. So they handle inheritance, they handle overriding, they handle polymorphism on types, that is generics. They handle polymorphism on qualifiers. We talked about that a little bit ago. They have this flow-sensitive type qualifier inference that some of you asked about when we saw it. That's noticing that even though you've declared something as non-null, as nullable, it's really non-null, so we'll just treat it that way. You can customize the defaults, you can suppress warnings, and there are a bunch of other features like that. So how usable are these things? They're integrated with the tool chain, best with Java C, also Ant and Maven. There's an Eclipse plugin that I've already told you about its strengths and weaknesses. NetBeans is built directly on top of Java C, so you pretty much get that for free. And there aren't that many false positives, and that's actually very cool. The false positives for the nullness checker are orders of magnitude worse than the false positives for any other checker. And the reason for that is Java programmers use null for so many different things. So a key issue here is that annotations aren't too verbose. For the non-null checker, over many thousands of lines of code, we found that there was one annotation in every 75 lines of code. And for the intern checker, we had a 220,000 line code base with 124 annotations total. Throughout the code base, it revealed 11 real bugs. As I mentioned, you can annotate as part of your program. New code has a lot fewer annotations. I just mentioned that. And we have inference tools for just 2 of the type systems, for nullness and for mutability. For the others, we're working on inference tools, but they're not done. So I've already told you about the caveat. You know that your program satisfies the type property and there are no bugs of particular varieties. That's not a complete guarantee of no bugs at all. That's future work. But the key is that this is only for the code that you actually check. So not native methods, not reflection. You can compile code with another compiler, and that will carry the annotations through to the class file, but won't do the checking. You are allowed to suppress warnings with a cast or with an explicit annotation, and that indicates exactly the code that a human should analyze. Relax about the rest, pay attention to the places where you've suppressed a warning. And checking just part of a program is still useful.
So you're saying you can annotate a part of the program to say, don't check this section of the program? Say suppress
well,
warnings, or?
typically, yeah. So that's a command line argument to the compiler. What I'm talking about here in suppressed warnings is, you know how you can write @suppressed warnings on top of a Java method,
Right.
and then it will suppress warnings in that. You can do the same thing here,
Okay, yeah.
or on a declaration, or in various other locations. And sometimes you need to do that. The example of, is this a legal SQL query was one I gave earlier.
So on the previous slide where you had the number of lines that were annotated, would you say the non-null, no, the next slide, the non-null, which is 1 out of every 75 lines, is that like the largest number of annotations? If you, on
No.
your programs where you use a bunch of these different checkers presumably, what's the overall 1 in n lines for all of them to combine?
So non-null is the most verbose.
Okay.
Non-null is not the most verbose. The mutability ones, we're seeing more like 1 per 40 lines, something like that. And remember, all the numbers I'm giving you are for existing code that has been annotated after the fact.
Right.
For new code, the numbers seem to be much lower.
So if you're going to take existing code and put in all of these different annotations, you might end up with on average 1 out of 20, 1 out of 30.
Yeah,
lines.
or 1 out of 10 maybe even, if you're going to use all of these. And you should think about which are the ones that are most useful to you. I mean, it's still not that bad. It's less than, for instance, the overhead for using generics.
Right.
Which you can decide whether that's something you want, right?
Speaking of generics, could you have implemented generics using annotations?
You could have, and it wouldn't be the right thing. I mean, the syntax of annotations is too limited. It would just be really, really ugly. And you'd have to have too much logic in the annotation checker that really belongs in the compiler. Okay, so the checker comes with an annotated JDK on the signatures, not on the bodies. So it's not checking whether there are any bugs in the JDK. It's just checking that you're using the JDK in the way the JDK is intended to be used. And I already mentioned that there are inference tools. Actually, the biggest difficulty with this really is you have some gargantuan third-party library you're using. You'd like to have guarantees about your code, but if you haven't annotated that library, your guarantees stop at the moment you go into the library. That can be discouraging. It's not as much of a problem for subtype qualifiers like non-null. It's a bigger problem for supertype qualifiers like immutable.
I am curious, have you guys thought about running the checkers against the open source parts of the JDK?
So we have access to the whole thing. It actually doesn't make sense to do that. And the reason is that the JDK is not even generics correct. So they took their pre-existing code base, they retrofitted signatures that were generic on top of them, but oftentimes the bodies don't type check. And we essentially make the assumption that your code is generics correct because we feel like that's even more basic. Once you have that, then you can think about this more advanced stuff. Okay, so I'll go briefly over how you might write your own checker. What time is it?
8:36.
Okay.
20-25 minutes.
20-25 minutes, sounds great. So how can you write your own checker? First, let's talk about security. This is an example of SQL injection. We have a bug in server code that creates a SQL query using unfiltered input. Here is the code from the server. It says the query is select star from users where name equals user input, and then you close the quote and semicolon, and it's all great. But the user inputs this. And now here is the value of query, where name equals A or T equals T. So this returns all the information in your entire database. This is not what you want to happen. In the box is the complete code of a checker for taintness. It's the whole thing. So if you want to use this, then you write tainted in your program. You can write untainted in your program. For instance, you could say get post takes an untainted string in category and then works on that. You would also need to find whatever validation code you have, annotate that properly, and that would probably include the one place in your code that has an unchecked cast. Now you compile your program. In this case, we're using a processor called the basic checker, which is why this one's so short, and it's using a qualifier named untainted, and now this will tell you where there are problems. So let's see a demo of that. So this is code from something called Personal Blog, which I found on SourceForge. And I've already added the annotations to it. Here's execute query. I say execute query should take an untainted string query because that's going to send that directly to session.find. And construct query also takes an untainted list of strings, and it concatenates them all. Now, the checker that you saw, it's 4 lines long. It doesn't understand when you concatenate a bunch of untainted things, you get an untainted thing back. So that's why we have this cast right here, and we've suppressed that warning there, because otherwise you'd get a warning. So let's see what happens when we run the checker on this. Well, we have category being passed in, and that is not necessarily untainted. So now you've got to figure out, should this be quoting it, or should this be taking something that's untainted? Well, after you've grovelled around in the code, you discover that this is what the spec should really be. So let's run that again. And now we get to here. This is a client of that other code. I just showed you that I was changing get post by category, and this is a client of that. It's sending in request category, and where did that come from? It came from right here. It's pulling it out of a user-supplied parameter, and it's carefully making sure that it is not null. But it's not validated. And if you go down to the end, you see that we have this validate routine. And the validate routine takes a user input and makes sure that it complains there's not a letter or a digit or white space. And now, then it just, if it throws an exception or it just returns, and if it returns, then that thing is untainted, which is why this returns untainted. So what we really want to do then is,
So, sorry, wouldn't you want to pass around tainted strings until you actually needed to use them? Because only then would you know how to untaint them.
so there are two possibilities. If you want to structure your code really well, there are two possibilities. One is the moment you get something from a user, untaint it right away.
But now you don't know what it's going to get used for, potentially downline from 50 method calls. So you don't know what untainted means at the point of receiving.
For instance, you don't know, is this going into a SQL query, is it going into HTML output, etc.
Right.
The other possibility is wait until the last minute. Both of these are really fraught with danger because you have a possibility of passing something through multiple places. The alternative is you actually mark everything anywhere in the code. You can use whatever policy you want, change it whenever you like. They're all marked as whether they're tainted or not. And here, tainted really means with respect to SQL. Here. I mean, and you might have a different type of tainting with respect to HTML, for example. So what we really needed to do here was to go up to
You're not using this for the SeaJUG website, are you?
what?
No.
So if we validate this,
Third-party tool, which probably is small bugs.
and then rerun it, then that eliminates the error.
And so you don't have to put the annotation on the declaration of that because it's just object. That makes sense. Okay.
I don't have to put
The annotation on the declaration of string request category
Oh,
because it's just the
Because it's called
object.
validate.
well, no. So this is an example of the flow-sensitive local type qualifier inference. Refinement, really.
Okay.
So we've said that it's tainted, but you're assigning something that's clearly untainted into it. So from this point down, we can assume it's untainted.
Okay.
Now, it would be perfectly correct and more explicit to write it here, but you don't have to. You don't have to clutter your code in that way. If you want to write it, if you think that's good documentation, then by all means do it. Totally legal. Doesn't affect the operation at all.
So is there a tainted annotation as well as an untainted one that just captures the opposite?
No, this is I mean, you saw everything there was to the checker.
So the
If you
tainted
want to
could be
augment
just-
it in clever ways, you can, such as adding that. And that's not hard to do. It's just more than 4 lines.
And in fact, that attribute, there was no semantics involved in it. It's just kind of a marker, right?
Yeah. So that's a very good observation. I'm going to get into that in just a slide or two. This is saying there are some strings that are blue, and there are some strings that are not blue. And all we're making sure is that the paint doesn't mix. Right? All the blue stuff says blue, and all the not blue stuff says not blue. And then we added either 2 or 3, maybe 3 casts in the program at the places where you're actually safely changing between the colors. Yeah, all the semantics sits right in this box. And of course, you would probably enhance this to understand some other things if you wanted to. Though this is useful already.
So you can use it on other things than string.
Absolutely, yes. I mean, it can mean whatever you like, right? Though, I mean, my recommendation would be that you should probably call this, untainted SQL or something, and then have another one whose definition might be identical for something else. Yeah.
What does that third line do? Does it fall trees?
So let me defer that for 1 second. Essentially, it says if you have a literal, starts with double quotes, ends with double quotes, written by the programmer in the source code of the program, that thing's untainted. We trust it. Yeah.
Your fourth line has a set of brackets.
Uh-huh.
There's nothing between them. Can there be things between them? And if so, what can be between them?
Yes, there can. So this fourth line is a totally standard Java 5 declaration of an annotation. And annotations are allowed to have fields, though they have to be written looking like methods. Yeah.
Just you could imagine like putting in a string array which has like untainted for SQL, JavaScript, whatever, sort of as an extension.
Yeah. Let me actually show you how you define a type system. I think this will answer some questions. Though if it doesn't, ask me again, please. So let's define the non-null type, the non-null annotation. So this first line is just standard Java 5. That's how you define a thing at non-null that you can then write in your program. A lot of Java programmers haven't seen this kind of thing, though. It's usually just done by library writers, sort of like wildcard. This is the way you say, this thing is a type qualifier. Now, if you want to define a type system, you have to specify 3 things about the type system. The first is you have to declare the type qualifier hierarchy. That's going to tell you all the subtyping relationships. The second thing is you have to declare type introduction rules. That's places where even when you don't write a cast or any other annotation, it's still there for you. And the third is all the other type rules, the special type rules, the places that an error can get raised. So let me show you how you do each of those things. First, the type qualifier hierarchy. Nullable object is the root of the hierarchy. Non-null object is a subtype of that. Nullable date is a subtype of nullable object, and non-null date is a subtype of both of these. Now, once you've declared this, ordinary Java type checking rules do almost everything for you. For instance, if you have an object variable, you can assign a string into it. If you have a string variable, you can't assign an object into it. Java doesn't allow that. Same thing here. If you have a variable that's nullable, then you can assign to it from an R value that's nullable. Sorry, from a date that's nullable, or from an R value that's non-null, but not the other way. So this already handles all inheritance, all method overriding, all assignment, all method call, all method return. Yeah.
So that explains why you don't just have a single nullable annotation with like takes like a Boolean true false. It was one thing I was wondering about. You know, why have this clutter and have a nullable and not null and not just one? But it's because of this.
You could do that. It would not work as well in our framework isn't designed for it, though we've done something like that in our framework. And I also think it's a little bit easier and a little bit clearer to write non-null or nullable rather than just one with a Boolean that you have to read. And that's a little longer too. But you could do the other.
Yeah, but then you wouldn't have the inheritance.
Well, you'd have to say nullable true is a supertype of nullable false.
Oh, you can do that.
You need to write your own code rather than our system doesn't do it for you automatically. So the way you say that is that non-null is a subtype of nullable. So that's how you declare this whole hierarchy. The next thing to do is type introduction rules. So if you say new date, or hello plus get name, or boolean.true, all of these things are non-null. They're guaranteed never to be null, these expressions. But you don't want to have to write that every time. So we say that this is implicit for trees, essentially, this is part of the AST. And
Right.
then for an expression that has new, that is creating a new class, or for the plus operator, or for any Boolean literal. And there's a ton more there. Then the third part is the other type rules, and this is where the real action happens. So for instance, we would like to warn if the expression in a synchronized block could possibly be null. Because if it is, you get a null pointer exception. There are actually a bunch of places like this where you might get a null pointer exception that people often don't think about. Another reason to use a checker. So we want to warn if that might be null. And here's how you do it. you write code in this case. You override a method in the framework called visitSynchronized that visits synchronized blocks, and you pull out some expressions from the AST. But here's the key line. If the type does not have the annotation non-null, then you report a failure, and this is just calling into the compiler error reporting. And then you have like half a dozen of these for dereference and for a few other places that you need, for the half a dozen places that you want to have that check. And that's more or less what it looks like.
So where does that code go?
Oh, so your checker consists of typically 2 or 3 different classes. One to declare the annotation, one to declare the annotation factory, which given an expression tells you the type, and one to declare the visitor, which is something that walks over all your code and does the checking. So this is part of the visitor. It walks over all of your code, and for every node in the AST does a check. And by default does nothing, but you can by default it just checks all the subtyping rules, but you can also add additional checks if you like.
So how big is the largest annotation implementation?
400 or 500 lines. And actually, so there are 4, I think, that are distributed with the checkers, and 3 of them are about 400 lines long, and 1 is shorter. And for instance, if you look at the Nullness one, the reason it's so big is because it has very sophisticated flow sensitivity rules. You don't need those. That was for the local type refinement, so that after this kind of if, then or this kind of call. And the reason is that again, people use null in so many weird ways that those rules need to be much more sophisticated for nullness than they do for any of the other checkers. Good question. Okay, so now I'm done. There are a bunch of research. Oh, yeah, I'm not done.
So real quick, the type rules. So before, when you were saying you're guaranteed, if you add in annotations, you're guaranteed not to have that type of error. That relies on your type rules being perfect.
Yeah, absolutely. That's correct. And so if you had gotten all the dereferences, but you'd forgotten the synchronized expression, you'd forgotten to check this, then if there's a bug in your checker, then the guarantee's not going to
use
hold.
only non-null annotations and everything in your checker.
Well, another part to that is if there's a bug in the code that you use to validate it or whatever to say now this really is not untainted, right? Then that's a problem too.
Yes.
Those are the 2 places, right, where you can screw up when you're using these.
Right. So the one is a user error. In that you have not checked some code you should have checked. Maybe you should have checked it by hand, or maybe you should have run the checker on it. And then this is an error on the part of, if you've forgotten this, that would be an error on the part of the person who wrote the checker. Yeah. So it's true. If there's a bug in the checker, then of course it's not going to give this as the guarantees.
So the checker is open source, so.
Oh yeah, you can read the 500 lines. Of course, it relies on a bigger framework, and there might be a bug in that framework, etc.
But you've run your own checker on your checker, guaranteeing there's no bugs.
Guaranteeing there are no bugs of certain types.
Never got a pointer, your null pointer checker doesn't mean that your null pointer checker doesn't check bugs.
Correct. Okay, good question, thanks.
Yes, the code, yes.
Okay, so there are a bunch of research results that pinhead professors get really excited about, and I like to tell them about that. You might not be as interested in this, but some people are very frustrated that practitioners are not running out to use all the type systems people have made up. That's because there have been too few case studies, because it's been too hard to build these things. So we've built new type systems, found things about old ones. There's this cool linear time inference algorithm, and there's a paper that you can read all about. I do a lot of other types of research. I'm interested in security, in programming languages, in testing, in analyzing version histories, etc. Essentially, anything that can help people to do a better job, because programming is tremendous fun, and it's more fun if you get it right. So the key takeaways are that there's this thing called the checker framework, and it lets you create custom type checkers. They're featureful, they are effective, they're relatively easy to use, and they're scalable. Now, I encourage you to go out and try them. If you have problems, let me know. We respond to bug reports, we fix things. I'm happy to sit down with you and try to figure stuff out. I'm not claiming that it's going to be perfect and it's going to solve all your problems. I've heard from some people who used them that they were really useful. Other people tried them out, said that's interesting, and it's not scratching exactly my edge. The cool thing about them is that they can prevent bugs compile time, and you can use the ones we distribute, like nullness and interning and mutability, or you can create your own if you want. And there's a download from this URL. So I know you didn't really get a chance to ask questions during the talk. So if you have any now, I'd be happy to answer. Yeah?
So the AST you're using in the checkers, that's directly the one provided by Java C?
That's correct.
Yeah, so like if you want to do port to, I don't know, Eclipse compiler, that's
Right. That's actually a weakness of the current implementation. So there is a, I think JSR 298 or 198 declares an AST that all Java compilers shall support. And it has been implemented 0 times, including by the proposer and by Sun that endorsed it. If that were implemented, then these things would port. Today, all the ASTs are a little bit different. So you would have to re-implement our framework to using the slightly different names of the different things in the different ASTs. So that's the reason that I was telling you that if you want to use this in Eclipse, you do that as an external builder. Yeah?
At the very beginning, I mentioned this once before, but you listed the various academic institutions that were creating more checkers for the framework. But where, and I noticed this is actually triggered by this MIT.edu URL that you put up there. Where's the home of this work? Is it here at UW, or is it MIT, or some? Where is the mecca for this?
The home is here. So the situation is that I was a professor at MIT for a little over 8 years, and in January I moved here because I thought it was a better environment for research and for teaching. So I still have students there. They're finishing up. I have not moved the URLs because I don't want to do that until they finish up to keep things convenient for them. But it will be moving. The stuff about the annotations is going to be in build 61 of OpenJDK. So the stuff about the checkers themselves, which is helping you define the syntax, the semantics, is not part of Java itself. If we're lucky, that will get shipped as part of the JDK. That is still under negotiation. It's open source, and you can download it.